we're talking about the Anfinsen experiment. Okay, so this is named after Christian Anfinsen, who discovered this in 1957. I don't know why it keeps blurring off and on like that. Okay. I wish the school would get us a new Elmo. That's another thing at Fort Liberty. Yeah, they got us the state-of-the-art Elmo, so I'm so happy. This is like...
It's good because their budget just got cut by $20 million in schoolhouse.
Wow. The JSOM or Campbell?
The JSOM.
So the protein that Anfinsen was working on was called RNase. Okay, so all we need to know about RNase is that it cuts RNA. Okay, it's going to cleave the phosphodiester bond in the RNA molecule. Okay, it cuts it promiscuously. Okay, it just cuts RNA, breaks it apart into individual nucleotides. So it's a protein that has a three-dimensional fold. Structure, function, and it turns out that this protein RNase has 8 cysteines. Okay, 8 cysteines, and those 8 cysteines are going to form 4 disulfide bonds. I went ahead and did a little bit more research after class on Tuesday, and I went ahead and found the disulfide bonding partner. So this is not something you need to know, but just for your information, we have cysteine 26 going to cysteine 84, okay, in the correct three-dimensional fold. We have cysteine 40 in the primary amino acid sequence, disulfide bonding with cysteine 95. Okay, we have cysteine 65 in the primary amino acid sequence, disulfide bonded to cysteine 72, cysteine number 72 in the primary amino acid sequence. And then we have cysteine 58 forming a disulfide bond with cysteine 110 in the primary amino acid sequence. And this is about, I want to say 150 or so amino acid proteins, okay? 150, 160. Right, so this is the correct disulfide bonding arrangement. So if everything goes nice and well, we would expect RNase A to look like this with those corrected disulfide bonding partners. Okay, 4 disulfide bonds. 1, 2, 3, 4. Okay, this is the correct three-dimensional fold. So what Anfinsen did, and so this is 1957 now, so people are interested in proteins and how they fold and refold and all this stuff. What he did was he denatured the protein. So we'll call this the folded protein, which we expect to cut RNA fairly good because it's a very, has a good enzyme, a good protein. Okay, what he did is he added chaotropic agents to them. Okay, so what are these chaotropic agents? One of them he added was 8 molar urea. Okay, do you know what urea does? Okay, it causes chaos. Okay, so what do we mean by chaos? If we look at the structure of urea, the structure of urea, those NH groups really disrupt hydrogen bonding because this has its hydrogen bonds. But you add urea or you add guanidium. Guanidium is the side chain of arginine. Okay. I forgot what guanidinium looks like. Anyways, whatever it is. So basically these are the guanidinium group, urea. All these basically cause hydrogen bonding partners to occur which disrupt this three-dimensional structure. So chaotropic agent he added was urea. There's a lot of them. Another one is the guanidinium group, which is the side chain of the amino acid arginine. Okay. So that denatures the protein, okay, because of the hydrogen bonding donors and acceptors here. Another thing he added was beta mercapta ethanol. Okay, we call it BME or beta ME. Okay, it's also called 2-mercapta ethanol. Okay, this is two nasty chemicals. 2-mercapto ethanol. So this BME or 2-mercapta ethanol has one function and one function only. Okay, what is that function? Okay, that function is to reduce disulfide bonds. Reduce them. Okay. It catalyzes disulfide exchange. Okay, so all of a sudden, instead of having disulfide bonds, okay, you have SH groups, thiol groups. So the disulfides get converted to SH groups in cysteine. Okay. So the 8 molar urea is going to denature the protein. The 2-mercapta ethanol is going to disrupt these disulfide bonds. Okay? This disulfide bond will be SH, 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 SH. So when you add 2-mercapta ethanol, 8 molar urea, or any other denaturing agent, what we have is a folded protein becomes denatured. Okay, denatured. These are also called denaturants because they denature the protein. So we'll draw this all denatured. Okay. Not only will they be denatured, the 2-mercapta ethanol will make those cysteines SHs. Okay, reduced. 1, 2, 3, 4, 5. So we're going to call this a denatured protein. Okay. Folded, unfolded. Okay. Folded, denatured. Now let's go back here to our 8 cysteines for a moment. Okay. Now we're studying protein folding, which is a interesting phenomenon that must happen inside our cells. If this cysteine 26 were to find its proper partner, the probability of that happening is we have one cysteine. Out of these 7, one of them is the correct one. Out of cysteine 26, okay, 7 of them, out of the 7, one of them will be the correct partner. So the probability for the correct disulfide bond to occur for the first correct disulfide bond will be 1/7. The probability for the second cysteine to find its partner, 40 to 95. That one, well, we got 2 of them off. Okay, so this one has 5. Out of those 5, one of them is the right partner, so it's 1/5. Okay, this third one, okay, has 3 remaining cysteines to find the right partner, and that's 1/3. And this fourth one, hopefully will find the right partner. Okay. So just based on statistics alone, probability alone, the cysteine finding its correct partner is 1/7. The second cysteine finding its correct partner is 1/5. The third cysteine finding its correct partner is 1/3. The fourth cysteine finding its correct partner is 1 because there's only one cysteine remaining. Okay, and I think you mentioned this, Mel. 1 times 7, 1 over 7 times 1 over 5 times 1 over 3 times 1 is 1 over 105, which is, and I remember you saying this, 1%. So we expect 1% of RNase to find its correct partners. 26 to 84, 40 to 95, 65 to 72, 58 to 110. We expect 1% of RNase just based on, stat 101 to be correctly folded. Okay? And of course, what was at that time, remember this is 1957, okay? At that time, what was shocking to him was that he found like 99%, okay? Almost all the RNase was folded. So let's go back to his experiment. He added a bunch of nasty chemicals, one of them being 8 molar urea, 8 molar. That's concentrated, okay? And this substance called beta mercaptoethanol, now the protein is all denatured. Okay. What he did next was he removed the BME, he removed the 2-mercaptoethanol. Okay, but he kept the 8 molar urea. He still had the nasty denaturant in there. He kept the 8 molar urea. Okay. So what he found was that so when you remove the 2-mercaptoethanol, what happens? Okay, you remove, yes, you're going to start getting the disulfide bonds form. Okay, but what happened was we're starting to get our disulfide bonds, but what else is there that's kind of bad? Okay, the 8 molar urea was there. Okay, so you still get a protein that's unfolded. Why is it still unfolded? Because of the 8 molar urea. But the disulfide bonds, as Courtney said, are starting to form. But the problem was they weren't finding the right partners. Okay, so 26 may have gone to 40. Okay, or 65 may have gone to 110. Or maybe this one was the right one. Maybe maybe 40, or whatever. Or maybe, okay. So maybe you had one correct disulfide bond. Okay, so you have here a combination of correct plus incorrect disulfide pairing. So 1, 2, 3, 4. Okay, this is called the scrambled protein. This protein is scrambling to find the correct disulfide bonded form. Okay, this is called scrambled. Okay, the protein is folding rapidly, but unfortunately, it's doing the disulfide bonds, but sometimes it has the wrong disulfide bond arrangements. Okay, so what he did then was he added back. Okay, so let's follow this. He added the trace BME back, 2-mercaptoethanol back. Okay, and we're still in urea. Okay, so when you add trace 2-mercaptoethanol, okay, he actually did this this is not related to the main point, but he kept it at pH 8, and he did it anaerobically or without O2, so absence of oxygen. Okay, situations that favor oxidation. Okay, and when he added back the trace to mercaptoethanol, he removed it. It got scrambled because it was trying to find the right cysteine partners. So it didn't find the right cysteine partners. He added a trace amount back, kept it into conditions where it would favor oxidation, and we still had the urea, so we still had that nasty chemical. But now what happened was, okay, we had the correct disulfide bond and pairing. Okay, we got 26 to 84. We had 40 to 95. 65 to 72, okay, and 58 to 110. Okay, so we got the correct disulfide bonding arrangements. Okay, so correct disulfide pairing. Okay, once you got the correct disulfide pairing by adding back the 2-mercaptoethanol and trace. Why did he add back the trace 2-mercaptoethanol? Yes, to break the incorrect disulfides and provide an environment for the correct disulfides to form. Okay, once you got the correct disulfides to form, okay, he removed the BME and he removed the urea. Beta-mercaptoethanol and the urea, and he got 100% folded. So if you give the protein the right environment, it will fold not 1%, but 99-100% of the time. Okay, how did he know it was folded? Because it did its job of chopping RNA. It cut the phosphodiester bond. Okay, whatever assay he used. Right, so that was his experiment, and our take-home point is this: the information that carries the tertiary structure of a protein is contained in what? What has the the amino acid? What do we call that sequence? What is the linear chain of amino acids called? Primary. Okay. So the amino acid carries the information for the tertiary fold. We call it the primary sequence. The primary sequence. So what allows this to fold into its three-dimensional structure? The primary sequence. In other words, the take-home point here is the primary sequence determines the tertiary structure. And back then, that was a big deal. Remember, we're talking about 1957. Primary sequence determines tertiary structure. Okay? If you didn't understand all of this, you want to just know this. Primary sequence determines the tertiary structure. Of a protein. Okay, and this is the dogma we go by to this day. Okay, so you denature a protein, it folds, given the right conditions, it folds back up to its native three-dimensional state. That means the instructions to allow that to happen is contained within the primary sequence. That is to say, the primary sequence determines the tertiary structure of the protein. Okay? Right, so that was the Anfinsen experiment.